Good afternoon, everybody. I'm glad to see you all here. The one observation that I was able to make, not a lot of young people here. Probably that is a little bit too low-level stuff for youngsters, but anyways, that's good. Somebody joined me on this presentation. So I'll be talking about U-boots on quite memory-restricted platform. And I call this U-boot bootloader for IoT platform with a question mark, so we'll see if it is feasible. So let me start then. First, I'll start from introduction. My name is Alexey Brodkin. I work for Synopsys as an engineering manager, leading a group of, quite small group of engineers doing development of open source projects for Arc architecture. And even if we are not talking about Synopsys, personally, I use open source software a lot in my spare time and doing my day job. So whenever I face a problem, I try to debug that, fix it, and I then contribute my fixes upstream. So that's how I got involved in a couple of open source projects, and some of them are listed here. The most notable of them, Linux kernel, Buildroot. Recently I started to contribute on OpenWrt, but regarding that presentation, what is important, I made a port of U-boot bootloader for Arc architecture a couple of years ago, and since then I've been maintaining that, enhancing, and all that. So that's our agenda for today. I'll start from introduction of my target platform that I'm going to talk. Then I'll explain what I had to do to strip down memory footprint so that my U-boot build is usable on that platform. And then I'll talk a little bit about how to execute U-boot from ROM, because by default this is not what usually happens. And in the end, I'll go through two issues I faced during first execution of my U-boot port on that board. So let's start then. U-boot, it is basically a bootloader, and is its main reason to exist to load some real payload and start it on the board. And typically it would be some kind of OS, it might be RTOS, or what at least here we may think of, it will be Linux kernel plus rootfs and all that. And initially I added support for AXS10X board, which was quite interesting development board. Basically that's it, but with a different CPU. What was important, it was 600 megahertz CPU with a lot of memory. You see these mentioned 2 gigabytes of DDR. Then I added support of that board with a little bit different CPU, which runs a little bit slower, but still I saw that it is more than enough for running U-boot bootloader. And so then last year we've gotten U-board, which is even more powerful. It is quad-core RHS38 CPU running at 1 gigahertz, and it has even more memory. And that is very typical situation when we use U-boot. It is a so-called single board computer. We use U-boot there every day. But there is such a thing which is called law of an instrument, or also known as a law of a hammer, which sounds like if all you have is a hammer, everything looks like a nail. And so that happens to me in that sense that whatever new boards I have on my desk, I try to port U-boot on that and try to execute it and see if there is some use of that. So that's what happened. I was given a new board with idea to use bootloader and package that into a real product that we are going to ship to our users. That tiny board, actually, it is quite small. It is like, you may see from connectors, it is like 3 on 5 centimeters or something like that. So it is called IoT development kit, and it is meant to be used as a platform for software development and debugging in areas like sensor fusion, voice recognition, face detection, and something else. And the idea to use a bootloader was to allow users to run their own applications without additional debugging tools. Like, you don't need to use JTAG whatsoever. You just build your application, put on an SD card or on USB storage, plug that into that board. You may see that there is USB OTG connector and there is SD card connector, but SD card slot, but probably you don't see it on the other side. And you may just run it without additional tools, which at least for me looks quite nice because you don't need any extra. That basically meant we needed a bootloader which may support these peripherals, may support FAT partition, which is usually used by developers on Windows machines. And here I think U-Boot is quite a good match. Now speaking about things which are important for U-Boot, like we see here that CPU runs at 150 megahertz, and from my experience with my previous board, I know that 100 megahertz is more than enough to start U-Boot as fast that you don't even recognize that it will be quite fast. But what differs a lot from previous boards is the amount of memory which is available on this board. So what we have here first is eFlash. This is quite an interesting flash memory which we may use for direct code execution right from it. So that's good, and it is relatively big compared to all the others, but the problem is you cannot write to the random address in this flash. To write there, first you need to erase a page, which means you cannot use it as random access memory. So we may use it for code storage, but we cannot use it for runtime variables and something like that. Then we have ICCM, which stands for Instruction Closely Coupled Memory. This is interesting on-chip memory, which is mostly supposed to be used for code storage. And we may execute code from there, but nobody actually stops us from putting data there as well. And so that's why for us it is pretty much normal random access memory, which is again relatively large here. Then there comes an SRAM. SRAM is SRAM. It is random access memory on chip, but it is quite a bit smaller. And so then here comes DCCM, which is pretty much the same as ICCM, but this is data closely coupled memory. And there is one but very important difference between them. DCCM is not connected to instruction fetch queue, which means we cannot execute code from that memory. And which means this is random access memory, but it is not very flexible. And so what I'm going to do on that board, I will use flash memory, which is not usable for writing data as a storage for our code, constants, and initially even data before it gets copied, and I will use DCCM for data which is used by U-Boot. That gives us possibility to allow user to use ICCM for loading their applications and starting their application from there. And if they want, they may use SRAM as well. But anyway, so once you load some application with U-Boot, you don't need U-Boot any longer, and you may reuse DCCM as well if you want. Also, we have SPI flash. It is good to store something, but again, this is not RAM, so it is not usable. As for peripherals on these boards, we have plenty of them, but in terms of U-Boot, what is important is SD card controller, and this is designware, mobile storage controller, USB OTG, this is designware USB OTG controller, and standard UART. So that's nice. And so why using U-Boot here? Again, we have support of pretty much everything here. You may see a lot of architectures, including ARC. We have support of different peripherals. We have support of that designware UART. We have support of designware USB on the O controller, and we have support of SD card as well. So nothing to do here. We have support of different file system, and FAT file system is here as well. So again, nothing to be done. What else? It supports networking protocols, but we don't have networking on these boards. But anyway, so that's an interesting benefit. And keeping all that in mind, it allowed me to add support for these boards, create that U port of U-Boot for that board literally in a couple of minutes. And you may see that's a change log of what I had to do, and I tried to highlight a couple of things. So what is important? So you add board here, you add device tree description here, and you add configuration here. So that's the minimal stuff you need to do anyways for any boards, and everything else here, it is only required if you need to implement some per board quirks, which I had to do. But anyways, this was quite simple. Now I said so that it was a working port. Well, it could have been working with the only important difference is we are not actually fitting in memories that we have. As you may see, resulting binary would be of size 400K, and we cannot squeeze it into 256 kilobytes of ROM that we have. So that basically means we need to do something about it, and we are going to work towards shrinking the memory footprint of that U-boot build. So what we may do, the simplest thing we may do, we may just go and tweak our configuration. Thanks to the fact that for quite some time already U-boot uses kconfig, the same configuration utility which is used in Linux kernel, it is a matter of firing up that like make menu config and then go through the options and disable stuff that we don't need. So for example, we don't have Ethernet controller, so we remove networking. We don't have, we are not going to start any operational system, so that's why we get rid of that as well. We are not going to load stuff through serial console because we have peripherals which are much more convenient, and we are not going to load L files because to load L file you need first to load L file in one memory and then extract sections from this L file to another memory. We don't have enough of memory to play with all that. We expect that user will load binary and just execute it. So we've got it removed, and already you may see we have a little bit different number here. So resulting binary will be smaller, but still we are not yet there. So what we may do else? Okay, we may try to squeeze a little bit of size with help of a tool chain. I understood that something was missing in our port of U-boot, and what it was that interesting feature when we asked compiler to put each and every variable and function in a separate section, and then we ask linker to throw away those sections which are not referred in any other sections. It is very simple thing, but for some reason, well, I know why, because previously I had way too much memory, so I didn't think about that. So I didn't do that, and so now I added corresponding options in CPP flags and LD flags, and if you want you may click on that commit if you download slides, and you'll see how it was done. And so then I realized that actually most of the other architectures, they already do that, except Arc, and for some reason another architecture where it is not supported is Microblaze. I'm not sure, probably toolchain doesn't support that because support is required, or probably it was never required because they always have a lot of memory. So with that nice thing, I was able to shrink another 5% of size, and we are getting even closer, but still we are not yet there. And the interesting thing for me was immediately, like you see BSS, which is more than 100 kilobytes. And BSS, it is basically not initialized statically allocated buffers. Like what's of that size? Okay, so let's do some analysis and see what that could be. And with very simple NM utility, I was able to figure out, okay, there are two buffers, each of which is 64 kilobytes. And so, well, that was not very good because I was very limited in memory. So when I started to look at them, I realized, okay, they are of size of this variable defined, which is defined. Fortunately for me, it was another configuration option. So what I did, I went back to configuration utility. I just set another size, and boom, I was able to save 100 kilobytes. And so already that allowed us to put that resulting image in our ROM, and we don't need already a lot of memory for data actually, because it is 7K here and 18K here. A little bit of background, actually that initial value of 64K, this is on a safety side, because in theory, FAT file system may have such a big cluster, but in reality, I don't think there are many cases when it is larger than 4K. So 4K is actually quite safe setting. At least for me, I was quite happy with that, but still, by default it's 64K, and if you have gigabytes of memory, you don't really care. So looks like we were able to significantly reduce our memory footprint. You see from 422 kilobytes to less than 200 kilobytes, which is quite impressive. And what helped us, the most significant result we were able to get after analysis of our resulting binary. And I used just size and nm here, at least that's what I showed. But also during my experiments, I used quite a lot blot-o-meter. That's a very nice utility which allows you to compare two different ELF files, and it will show you how different symbols became bigger or smaller, and how much of the memory you were able to save. Like it will show you now you are plus 15% compared to where you were before. Another thing which helped, I was practical. I just removed all the crap that I didn't want to use, and so with some tweaks of a toolchain, I was able to save some space as well. What could be also tried, it might be LTO link time optimization. I tried to play with it a little bit, but for that I needed to make a bit more changes to U-Boot build system, because link time optimization requires to use GCC driver all the time, even when we invoke linker or archiver or anybody else. And so that requires more changes, and I didn't expect to get a lot of achievements here, and I was already achieving what I wanted to have, so I just decided, okay, probably that will be the next exercise. So, like, we are pretty much done, but there is another thing. We want to execute U-Boot solely from ROM, and this is not what usually happens. Usually, U-Boot gets self-relocated. Probably not all of you know about that, so I'll try to show you what happens there. So that's what happens. First, we load U-Boot into some initial location. It might be ROM, it might be even start of the RAM or some other location. And there we load entire image. And then what happens, U-Boot gets copied in the very end of available memory and start to allocate needed memory for heaps, stack, environment, and something else. This is required because on some platforms, for example on x86 and on many others, you don't have DDR prepared for usage, and you have to set its clocks, you have to train it and to do something else, which means you need to execute from some safe location which is not DDR. For example, in x86 what they do, they lock a couple of cache lines and execute from there. It is not something people may expect to happen, but these hacks are really happening. And then, even if you start from the very beginning of the DDR already, if there was a pre-bootloader, which we have, for example, on our boards that I mentioned before, you want to still move U-Boot here, because in the beginning of the memory, you'd like to put real payloads which will occupy entire memory when U-Boot execution is done. So there are a couple of reasons for U-Boot to relocate. Well, and actually there is another reason, because our data is still somewhere here, and we cannot write to this area when we are in ROM, which means we still need to relocate at least data, and that will be still a requirement for us. And anyways, that kind of relocation works quite fine when you have a lot of memory, but in our case it looks like that. You see the difference? So that's a U-Boot bin, and that's our available random access memory, which means most probably we won't be able to copy ourselves together to that area and do something else. So we need to keep everything that we can in ROM and only put required stuff in RAM area. So what we need there? We need to have heap there, essentially stack, data, environment, and we will load payload. But we are not going to squeeze payload here because we have a separate location for that. But that's just for a generic case. And for that to happen, what we need to do, we need to skip relocation. Even though it sounds quite simple, it requires quite a few architecture-specific fixes in generic codes. It doesn't work right away. Because different code paths should be used, and even though there is a generic flag which we may use to say that we want to skip, but then we still need to have a couple of defines here and there. Again, if you download these slides, you may have that link where you may find all the changes I had to do. Actually, not that many, but anyways, that had to be done. So once we have that modification, we signal in our platform code that we don't want to do that relocation, and we only will do some data copy later on, and then we may execute from real ROM. And let's see what we need to do. Initially, we have our entire U-boot bin. So where's the pointer? Okay. Initially, this is our ROM, and we have everything here. We have interrupt vector table, we have text section here, we have raw data, and even data here, because this is our initial U-boot bin, because data, it is initialized data. We cannot just get rid of that. We need to still have it even before we start execution. And then we need to copy data somewhere in our RAM. It sounds simple thing, but there are two questions we need to answer first. First, question is, okay, so we need to copy data, but where are we going to copy that? Because we have a relatively large RAM, and at which location? In the beginning, in the end, or where? The second question, okay, so how can we have such a strange situation when linker creates U-boot bin with data here, but then we move somewhere, and from this code, we still may refer to variables, for example, in that array in completely different memory region. So let's try to answer that. So to answer the first question, we need to understand what U-boot does during initialization in terms of memory allocation. First thing it does, it essentially allocates its space for itself if we are going to relocate. So somewhere here it would be place for entire U-boot binary. And in fact, it was happening even if we signaled that we wanted to relocate. If we wanted to not relocate. So I had to change that and not relocate that again. For bigger platforms with more memory, we don't care, we allocate here 200 kilobytes, here 200 kilobytes, and don't care. But here I have to be very careful. Then once that allocation done or not done, we allocate space for environment. And we know the size of that allocation because it is specified in our configuration header. You see config underscore, it is either kconfig variable or something set in our configuration header. Then we allocate space for malloc, we sometimes call it heap, and again we know its length already. And also what is important, we need to allocate somewhere space for a stack, and this is done by simply pointing to initial stack pointer allocation. And in my implementation, I decided to put it here in the very beginning of the RAM. And there is a good reason for that. And on the next slide somewhere, I will explain what was the beauty of putting stack here. So from that picture, I think that's clear. So if we use that value, which we all, anyways, as I mentioned, set in configuration header, we may use it as a point where we load data. So that problem is solved. And answering the second question, how we deal with data which is linked here but then copy it here, it turned out that GCC GNU LD may already do that, and they use concept of different virtual address and load address. If you are interested, again, you may follow that link and get some more information. But what do we need to do for that? Unfortunately, that's not the very good position for me. So first, we define two different memory regions. So this is a ROM, and we set its origin and size. And this is RAM. Again, we set a region and size. And then for each and every section, we tell linker where to put it. So for example, IVT, text, and raw data we put in ROM, and that's the interesting part. We ask linker to put data in RAM, but then put it in ROM. And what happens, we use addresses which match those addresses. So compiler used some addresses to access stuff in that section, but linker will put it in a different area in expectation that it will be copied to virtual addresses that we used during compilation, later on during execution startup. And yeah, then there is a BSS section which we don't put somewhere in ROM because we don't need it there, and it won't even appear in our U-boot bin because BSS, it is nothing. We will just allocate some memory region in runtime and will zero it. So we don't need to mess with that. What is also important here, we put a couple of link time defined symbols. For example, this is RAM start, RAM end, BSS start, BSS end. This will be required, and this one is also important, by the way, ROM end. This will be used for runtime tricks we are going to do early on start. And here you may see how I calculated a couple of different values. It requires some time to understand what's going on there. So I wanted to do that thing. So RAM data size, this is not the entire size of the RAM, but this is size which will be used by exactly, where's the pointer? Data, BSS, heap, and environment. So this is that area, but not entire RAM and some other variables. And that's what we have in memory layout if we use variables or constants we define by a linker. You see, this is ROM-based, so this is quite clear. It was a text-based before. This is ROM ends, and this is important because that's real address where data exists before copy. So that's the place where we use to start copying data. And here you see RAM start is a location where we're going to copy. So basically we copy in a cycle everything from here to here. And so we know the size as well. We may calculate it even during compilation, and so that is very simple. And we know as well a location of BSS, so we may easily zero it later on. And that's what we need to do basically. First we set that flag, GD flag skip relog, and so I'm doing that here, and note to the name of the function which is executed very early on startup. So we signal that we are not going to relocate, then we copy data with use of those symbols that we defined previously. And so finally we zero BSS. Actually, it is not entirely correct. It will happen in a different function. So I put it here as a matter of demonstration. But this step happens anyways, even if we do relocation. So looks like we are ready for the first execution of U-boot on our board. And yeah, and now we are going to execute it and see what's going on. So in fact, console works, but not everything working as expected. So we want to start using USB, and first thing you need to do, you say USB start. And what happens? Well, it says error -12. Like what? Okay. And error -12, essentially this is mem, which means we don't have enough memory during allocation in our heap area. And what helps here, if we take a look at our backtrace, we may see a couple of interesting things. So we start USB initialization, then we do device probe, and then we do allocate prev, which at least for me hinted that each device has its own private structure, which is used for storage of device-specific information. And I thought, okay, so if I look at corresponding driver at its private structure, probably there is something interesting. And indeed, I see there is some buffer of size, DWC, data buff size. Okay, and if we look at its definition, we see that indeed this is another 64K. And then after quite a short discussion with Marek, he hinted me that actually this is not a strong requirement. This is a buffer which is used for data exchange via USB, and we actually may make it much smaller, and even if we want to transfer a larger amount of data, it will be just split in a smaller buffers, and that's fine. And so what I did then I added another kconfig option which allows you to fine-tune that value to whatever you want. So 64K was way too much for me, so I set 16K, and since then it was working perfectly fine. What helped here, that I was able to look at the backtrace and well, actually some knowledge on how drivers work in modern U-boots. And so this driver is DM, so what is it? Driver model implementation, because if you use legacy implementation, it will work a little bit differently. So now when we get that thing fixed, I faced another issue when I tried to access finally FAT file system. So what I saw, it was quite interesting because nothing happened. Fortunately, I have access through JTAG to that board, and I saw, okay, I'm in memory exception. So how come that memory exception happened? And so then I took a look at registers, and what I noticed that my stack pointer register, which is a separate register, at least on our CPUs, pointing way outside of our RAM area. And if you return to that slide, you see, so it was pointing somewhere here. And that is the beauty of stack being here, because there is no memory here, and my memory subsystem just returned an exception. If I have put that stack area somewhere here, for example, after data, you may imagine what would happen. I would silently start to corrupt my data, and somewhere later down the line, like during execution of something else, I would face significantly worse situation when I need to debug something which might not even be reproducible easily. So that's why you either put it here and expect an exception here to get when you access in this area, or if you have like memory protection units, you may use it as well. It will definitely help. Yes, so also what may be used as a hint, so yeah, we understood what was the reason, so then, well, not the reason, what's happened. And what was the reason? Again, if we look at a backtrace, we see that last function which was execution is part test DOS. And in that function, if we look at that, we see in the very beginning allocation on stack indeed of something. This is a couple of macros which are wrapped around each other, and in the end, that thing, if simplified, looks like that. So what it does, it allocates memory of size of that structure multiplied by amount provided here. And here sector size is 512 bytes, and it is like what it is, 78. And if we multiply that, we get 40 kilobytes. But if we look at that function a little bit down, we see that actually what we want to do, we just want to see file system magic number, which occupies like a couple of bytes. We don't need actually 40 kilobytes here. And when I took a look at the Git history, I understood that there was a previous fix that changed allocation function from something else, and semantics of that function was different. And actually what that guy wanted to do, he wanted to put here 1, because we want to allocate only size of that structure. And with that fix, which is mentioned here as well, I've got this problem resolved as well. And so from that exercise, I concluded that you have to be very careful when you see something like that, because if your memory restricted a lot, you may allocate that here a little bit more than you expected. So in the end, I've got a working system, and so those goals that were mentioned in the beginning, they were met, so you may now load image, start it, and play with that, with anything. And basically the main conclusion of all that exercise is U-Boot is perfectly usable on a platform with not that much of a memory. Like for this particular case, I was able to squeeze it into 200 kilobytes of ROM and 100 kilobytes of RAM. And still with that, I've got drivers for serial ports, USB, MMC, and support of FAT file system, not even for reading, but for writing as well, because we expect a user to keep an environment on SD card or USB storage. And if you have tools that really helps a lot when you are trying to analyze where you may strip down memory a little bit more. Still, sometimes you need to either enhance existing generic U-Boot codes, or sometimes even fix stuff because things are done wrong in some places. But anyways, that helps. And what also is good to remember that when you are fighting with limited memory situation, allocation happens not only statically during compilation, but in runtime as well. And it happens not only in heap, but in stack as well. And it is always very complicated problem when you have stack overflow. Another thing that I want to mention, in that particular situation, you need to bypass U-boot relocation, and unfortunately that requires some work if you are not using ARC architecture, which most probably you don't do, because there are not that many boards with that architecture, but hopefully at some point people start using it more. You need to patch code and hopefully send patches in upstream as well. And yeah, the last conclusion is most of runtime problems are due to problems with memory. So I think that's pretty much it that I wanted to tell you about my excursion with U-boot on that platform. Thank you all for being here and not leaving me here alone in the middle of this session. Any questions so far? Yeah.
At the very beginning, you started removing some features unnecessary, and you removed an ability to boot any operating system. So yeah. What this bootloader will do after it will boot? So what's the purpose?
The world doesn't tend on the operating system, right? Mm-hmm. The point is you build your bare metal application, which does, I don't know, sensor fusion, whatever. And it is 100K in size, I mean entire binary. You may produce with a compiler not only ELF file or a UImage, you may build image, binary image of your application. Then you load it into memory, so if we return even further, so you load it, what is my pointer? So you load it, say here, your application, and execute it and do whatever you want. With U-boot, on U-boot parlance, what you do, you say fat loads mmc0 mycool_app.bin and provide address. And then what you do, you say go to the same address. And what happens, U-boot just jumps to that location and starts to execute your application. Uh-huh. From this point, there is no U-boot any further. It might still exist somewhere, but you pass control to a different application, and so that's the reason for bootloader to exist.
So this option doesn't prevent from running a bare metal, raw binaries. Sorry? So this option doesn't prevent U-boot from running bare executables, right?
Again, what is the question?
This option doesn't prevent U-boot to run.
No, that is a very specific option which does quite a lot of things in preparation for starting Linux kernel. Yeah, and then loading stuff, changing like device tree blob IPs, and then doing a lot of checks, prepares registers, caches, and then passes control. Go command is very simple. It is implemented as jump.
Okay. Thank you.
I have a really simple question. How small can you actually make U-boot be, the binary? Can you strip it down, say, to 64 kilos? Is that possible? Is there some mechanics for that?
Yeah, you see what I had to do here. I had those limitations.
Right.
Unfortunately, actually in the beginning I was not 100% sure, but I said, okay, I will do that. And fortunately I was able to squeeze what I have in, what I wanted in what I have. But can we go even further? So if you take a look at...
yeah, so if you like remove the USB from the file system and so on, how small can you get?
Well, I need to try. Again, I had to implement something which supports both SD and USB, and essentially it takes especially USB, I think, and file system, it adds quite a lot. But then the question is, if we remove all the peripherals and leave only U-boot's core, why do we need that?
It's just a thought experiment, really. How small can you get?
Well, yeah, so we may...
Well, actually, there are systems that have SRAM limitations.
No,
and you need to load U-boot into that and execute it.
But for that case, we have, SPL, we have all those tricks which will strip down all the print case, printfs and all that. So, yeah. That will be the thing I would use in that situation, that's for sure.
Can you speak about that a little bit, about SPL?
Well, it was not implemented here because it is not what we wanted, because SPL is not meant to be used as a full-blown bootloader that we wanted. It does one simple thing, but I think you know it better than me, right? You're kidding.
No, I actually want you to say that to the audience about SPL.
Okay. So
I'm trying to guide you there.
The spoiler is we may have even more stripped down U-boot, which does only one thing that we want it to do. It loads from only one media typically, and doesn't throw debug messages. But it is very tiny, so it could be fit in like one page of something. And for example, I think on IMX platform, what they do, they have SPL, which fits into one page of memory, like 4K or something.
No, it's 32 or so.
Oh, 32. Well, anyways, it is quite small.
I do believe you can make a boot as small as one jump instruction.
No, and what Marek was saying about it is a practical thing, because what happens, you have a multi-stage boot. First, you have boot ROM, which actually does pretty much nothing. It might be a couple of lines of code which copy stuff, for example, from SPI word by word. Then you start execution from the first page, or from, for example, as on x86, you have cache lines in which you log, you load, and you have 32-bit K, no more. Then you start execution from there, and then with SPL, you initialized your DDR, and then you may load real full-scale U-boot from SD card from that DDR, because you already have driver for SD cards and file system, which you are not able to have in a pre-bootloader because you only had a couple of lines of code there. So you see, on each stage we are becoming more and more powerful, and in the end we may do whatever you want. So that's a beauty.
Hi. So what's your long-term plan here for maintenance? Is it all going to be upstream?
It is already there.
It's already upstream. Okay. And are you going to maintain these options going ahead?
These options? Which options do you mean?
The options to be able to strip off different features and strip off...
Well, you can strip features yourself. That's configuration for your boards. Well, that's my board, that's my configuration. If somebody wants me to add another feature, okay, I may add it. If somebody says that we don't need USB there any longer, I will just strip it down. Essentially, I will support that because I'm a maintainer of architecture. That's my board, so it's my responsibility. That's my sort of a child.
The framework-related stuff as well, where you create each symbol goes to a different section, and then you strip off at the linking time, where you realize what the symbols which are not being referenced anywhere, and then you strip it off. I would guess that will be at somewhat more framework level rather than your platform port.
Yeah, as I told, it should be generic feature, but probably back in the day it was not supported. I know that for Arc it was not supported a couple of years ago, and so then it became supported by, I only added that feature now, because again, for previous solutions it was not needed, I had enough memory. And for example, microblades, we may ask Michal Simek, I think I saw him, if he just didn't think about that, probably that's the reason. And if it is possible to be done on microblades, then it is no-brainer. We should get it into generic code, and actually that's a good idea, but first we need to figure out what's wrong with microblades. So yeah, that's the next step, indeed. Okay, thank you very much.